Find. Yesterday I was looking for the book.
If you can find it, there's extras that are floating around, but you need to get the book. So if it ran away, there's enough of them around. You can steal Steinmacher. Steal Steinmacher. Steinmacher passed, so he doesn't need his book right now. Where's everyone? She was here. Where'd you go? Sometimes you're like herding cats, where like one of you appears and the other one disappears. Anyone do anything fun or interesting? Everyone survived the snow? Surviving the snow apparently was an issue. Apparently Hope Road was really bad the last couple days.
Yeah, it was.
It's so strange how localized it was that some towns got hit by snow yesterday and Monday and some didn't. It was kind of strange, and particularly if you're watching in New Jersey, you can either get the Philadelphia news or the New York news. So if you watch the Philly news, it's like, it rained. If you watch the New York news, it's the end of time. It was kind of strange.
It's just too hard to get out of here. I'm just going to call out.
Just
1 hour.
They'll find a cop for you.
Give me 1 hour to go to the park. Yeah, 1 hour from here to there.
So that's one of the things that we'll be discussing in the second slide deck is special cause variation. So special cause variation is the case with assignable cause. The weather was really bad. So in general, how long does it take you to go get home?
2 hours.
No, how long in general on an average day? 25 minutes, right? And Sheldon Dean, your lovely quality guru, actually does a control chart for his commuting time every day coming to work. Yep, he does an eye chart, which will meet why he does an eye chart, and he does it every day. He has an old Excel file that updates. So if you really want to be cute, go bother Sheldon and ask him about that. So obviously, yesterday, since it took you so much longer to get home, that would be a case of special cause variation because there was assignable cause. Something weird happened. Well, Hope Road was an ice skating rink, and that's why it took you so much longer. That doesn't always happen. So we'll talk about process stability being predictability. So if you wanted to make a prediction of how long it's going to take you to go home today, you wouldn't expect to see that variation because, well, there's something weird that happened there. Hope Road was an ice skating rink. I just drove down Hope Road. It's not an ice skating rink. You should be okay. So that's the idea of use control charts to see, is my process in control? Is it stable? If I look at my process today, is it a good predictor of looking at my process tomorrow? And that relates into process capability where we were. So before you can even look at process capability, you have to show that your process is in control. So that if I look at it today, it's a good predictor of what it'll look at tomorrow. Because in process capability, what we're trying to do is we're trying to answer the question of what's the probability, what are the odds, how likely is it that I'm going to produce a good or deliver a service that's going to meet or exceed my customer expectations. So what process capability tries to do is it tries to relate the voice of the customer, described by the upper and lower specification limits, and relate it to the voice of the process, where the voice of the process is actually what your process does. So as we talked about in our descriptive statistics, there's generally two ways to describe data. One is to describe the measures of central tendency. So anyone remember what the measures of central tendency are? No. The mean, that's one. The mean, the median, and the mode. Very good. So we can describe our data, the way our process is performing, based upon the mean, the median, and the mode. Cool. And then we can measure the dispersion. So how spread out it is. How, well, on average, how far is a given observation from that average? Anyone remember what the measures of dispersion are? Sorry. It's a couple of them. Come on. Get the juices flowing in the brain. Come on, it's already 10:30. You guys have been at work. Standard deviation. So when we know standard deviation and the variance, right? Because those always can, you can use one, you can use the other. Because we remember that the variance is the standard deviation squared. Cool, so that's two. Anyone remember another one?
Range.
Yes. And related to the range is the interquartile range, right? Cool. Someone look back in their notes. Remembering that the exam is open book, open notes. You can use whatever handwritten notes you have. You can use the PowerPoint slides. You can use a Holy Book if you think that'll help. Kidding aside, I did have one gentleman who English wasn't his first language, so he brought a dictionary with him. English to whatever his native language was dictionary. So you're allowed to bring that. So if that's going to help you get there. But again, when you're practicing for the exam, it's coming up. It's creeping up on us. June 7th, it's coming. Weather will look a lot nicer if we won't have snow outside, hopefully. But be prepared for that. So you're able to look back in your notes and see that there's the mean, the median, and the mode are the measures of central tendency. Our measures of dispersion are the standard deviation, the variance, the range, and the interquartile range. Cool. Okay, so process capability. What we're doing is we're relating our specification limits that come from our customer. So where does our customer get the spec limits from? Yeah, where do the spec limits? How many of you have seen spec limits on things? That's okay.
I like it far.
Okay, you're like,
It's my
then you
face.
can go all the way in the corner. Go in the corner.
That's good.
Go in the corner.
Okay, good.
What you get? That's your reward for coming in late. You get to sit in the corner. Okay, so where do your specification limits come from? The customer. And how does the customer create these specification limits? Do they look in their holy book and then there's something from on high that says,
I think it was random or maybe expectations from deliveries and quality.
say that again? I'm sorry?
Production, deliveries and quality.
So it establishes what quality is. So
Yeah.
quality, most broadly defined, is whatever is important to your customer. And we're talking about this all being important to your customer. So what were you saying as your definition of where your spec limits come from?
Customer expectations
Okay.
for the quality product
Okay.
basically reflects back to the specs.
Okay, so, but where does the spec get established from?
From the studies maybe. or
Okay.
that products. But not all the time studies, because last time he told us that the 2000 calorie.
Yeah, it just came from, correct. And that's a lot of times where specifications come from. They're sort of arbitrary, but they're the standard. So the fact that a meter is arbitrary, but we accept it as the standard. And we've defined the amount of a meter as being the amount of distance traveled by light at a particular wavelength in a particular period of time. But the mythology is that was the standard length of a Roman soldier's step. Doesn't really matter where it came from, but that's the standard. So the specification, sometimes there is a very good reason for why the spec is what it is. Sometimes it's arbitrary. Sometimes it's excessive. So what's the spec on our number of CFUs on a product? Depends. So what's a typical limit? One CFU?
Aseptic processing should be basically 0.
Yeah.
And then up to I think 1 is error.
Mhm.
Just talked about, I mean, here that's what I see.
Yeah.
2
So,
and 3 are actions.
so why is that? Does it mean that we find 1 CFU on something, it means the product's contaminated?
No.
You find 2 CFUs on it, does it really mean it's
No.
contaminated?
No, you have to evaluate.
Yeah, and again, all bacteria isn't created equal. A lot of it is just happens to be there and it's going to be perfectly biocompatible and not cause adverse health effects. Some of it is. And there's some interesting challenges as you go to classify that data if you have multiple microbial contamination of the same thing, which is likely. So what's going to happen is if you have a sample and you have 2 microbes hanging out in that sample and a limited amount of food, they're going to compete, right? They're going to end up Darwinian survival. Only one's going to be there at the end. So then when the lab goes and looks at it, they're only going to see the stronger of the 2, even though there was 2 originally there. We got someone on this side.
You don't have to turn that camera, that's.
That's perfectly fine. You like?
I don't like to be in it. I heard last week you turned it.
I did. Well, that means that someone watched the video, so at least we're getting somewhere. So when it comes to the specification limit, sometimes they're arbitrary, sometimes they matter. Sometimes your specification limit, when you stop to think about it, kind of doesn't make sense. And it's something that you always need to be aware of is that what specification limits matter, what specification limits are arbitrary, and what specification limits aren't really measuring the right thing. And that encourages you to have a dialogue with your customer to say, hey, is this really what the specification limit is? But the spec limits come from the customer. Doesn't mean you can't ask the customer to change what they want, but it comes from the customer. So when we're talking about process capability, we're talking about our process and how well does our process deliver based upon what our customer wants. So the first of those indexes that we talk about are CP and PP. So in the case of CP and PP, it's our easiest of our two ways of looking at process capability. We only need to know two things. We need to know our spec limits. Appears to be some ice broke off. Or is the spec limit coming down from on high to tell us something? So we need to know our spec limits. Those come from our customer. So they'll give us our tolerance zone. Tolerance zone generally being the difference between the upper and lower specification limit. Yeah, we're just wrapping up lesson 5 because it's important stuff and it relates directly into our control charts. It's amazing. I sent those slides out late and people got them. That's always cool. So, and it relates to the standard deviation. We'll get there. We'll get there. We should fly through this because it's just so important. I wanted to reemphasize it. So it relates that to the standard deviation. So the standard deviation is based on our process. In the case of CP, it doesn't account for where the center of our distribution is. So it's only looking at the dispersion. And it's relating the dispersion to our spec limits, which only tells part of the picture, right? If you look at the two graphs up there, we have one where the blue distribution is right in the center of the spec limits. So we'll get a high CP value. And there's a high likelihood we will produce something that our customer will accept. Then if you look at the bottom of those two, we have the same blue distribution. But based upon the bottom one, what's the likelihood we're going to have a satisfied customer? Basically 0, right? But we're going to get that same CP value because the CP value is just looking at the ratio of the spec limit to the dispersion. So in many cases, it doesn't tell this whole story because the idea in process capability is that we are trying to predict what the likelihood is that we will meet or exceed our customer expectations. So in this case, we might get the wrong answer. We might make a bad prediction. So the answer to that is with CPK, which is on the next slide. So in the case of CPK, we need to know a little bit more information. We need to know the tolerances from our customer. We need to know the measure of central tendency, the mean, and we also need to know the dispersion, the standard deviation. So what CPK and PPK do is they look at the distribution and see where is the center of the distribution relative to the spec limit. So is the mean closer to the lower spec limit, or is the mean closer to the upper spec limit? And then dividing by 3 standard deviations. In the case of CP and PP, we're dividing by 6 standard deviations because we're looking on both sides. In the case of CPK, we're only looking at one side, either less than, we're closer to the lower spec limit, or we're closer to the upper spec limit. Everyone cool with that? So to calculate CPK, we need to know the spec limits, the standard deviation, and the mean. And there are different ways to approximate the standard deviation. Only for the purposes of process capability. If this were the black belt exam, we would spend a little bit more time on this differentiation. Forrest Breyfogle III, who is a very odd gentleman, who I've actually gotten to know a couple times. He generally speaks opposite me in conferences. Has written several papers on why using other methodologies for calculating the standard deviation for the purposes of calculating process capability is a bad idea. But just know that there's different ways to approximate the standard deviation in the case of process capability and process capability alone. So there's a difference between when to use CP and PP. One relates to potential process capability. And the good news is for your exam, they won't ask you a question on this. It turns out that the automotive industry uses it in CP to represent one property and CPK to represent another property. Other industries do it differently. Since the Green Belt exam is designed to be industry independent, and different industries approach it differently. You won't be asked a question about when to use CP versus when to use PP. Good news for you. One less thing you have to worry about. But you do need to be able to calculate it. Okay, so how do we use it? So if our CPK value is between 1 and 1.3, we're doing pretty good. And if we're greater than 1.33, we're great. Again, this represents an index. So processes with lower capability are the ones that you should target for improvement. Processes with higher CPK or PPK values are better performing. They're more likely to produce a good or service that meets or exceeds your customer expectations. Okay, typical exam type question that requires some thinking. Actually, I think this might be one of your tri-term exam questions. The relationship between CPK and CP is best characterized by which of the following. CPK is always greater than or equal to CP. CPK is always less than or equal to CP. C, it depends on the data. Or D, I can't think of a D off the top of my head. It's not D.
None of them.
Yeah, none of the above. Okay, so what is the relationship between CPK and CP? Which has to be larger? Is CP larger or CPK larger? So let's look at our definitions. There's the definition for CP. Our upper specification minus the lower specification over 6 sigma. And in the case of CPK, it's the minimum of the upper specification limit minus the average over 3 sigma, or the average minus the lower specification limit over 3 sigma. So pick the smaller of the two. So the question is, which is always larger? Or which is always smaller? Or is there no relationship? What do you think? Okay, who thinks CPK is always larger? Got one vote for CPK. CP. Everyone's got a vote. One. Okay, you don't understand the question.
I'm trying to figure out.
Okay, everyone's cool with what the question is asking, right? We have 2 indexes for measuring process capability, CP and CPK. My question to you is, what's the relationship between those indexes? Either there's no relationship, that sometimes CPK will be larger, sometimes CP will be larger, so that's option C. Or there's the option that CPK is always larger, or that CP is always larger.
CPK is the number.
Let me frame the question a little bit differently. When are these two things the same? When are they equal? When it's exactly in the middle, right? When the mean of our process is exactly in the middle of our spec limits, CPK and CP will be equal. Absolutely. Because CPK is looking at which of these am I closer to, and dividing by 3 sigma. So in the case of CP, we're assuming we're in the middle, and then we're dividing by 6 sigma because it can be off on the left and off on the right. Okay, so now we know when they're equal. So anyone want to change their answer now that we've defined when they're equal? Okay, so I don't remember which I said it as. CPK being larger? Still saying CPK being larger?
Depends. I don't know if I wrote them down the same word.
I remembered what you said.
We have video. We can go back to the video, but let's hope we not do that. Okay, so who thinks CPK is larger? CP? Okay, I'll let you know. It depends. It's probably the one time I'll ask a question and the answer is it The answer is not, it depends. Okay. So everyone's got to vote. So we have one vote for CPK. CP. Okay, so the majority goes with the CPs. Why are the CPs? Convince the CPK why it's CP.
Centimeter and then divide specification, centimeter and divide by 6.
Okay, the relationship between 6 and 3 is just because in the case of one, we're looking at both sides, and in the case of the other, we're only looking at one side. And the normal distribution is symmetric, so that isn't going to carry the day. And we saw that if it's in the center, exactly in the center, the values are going to be identical.
Oh, the next CP has been,
Yes,
because of, you're doing the upper minus the lower versus the mean versus.
exactly. So in the case of CP, K, it can only be smaller than CP because the best possible, the best possible circumstance is you're dead in the center. And when you're dead in the center, you've got CP. So CP is always going to be greater than or equal to CPK. Because CPK takes into account the reality that the center of your process isn't necessarily going to be in the center of your spec limits. Because one is your process exists. Your specification limits come from your customer. Generally, they don't know what your process is. Everyone cool with that? Kind of an important concept. And I'd be shocked to see if you don't see some variant of that on the exam. See, that's not a math question, but it's a thinking question. Involves some thinking about math, but it doesn't involve using your calculator. Okay.
Short and long.
Okay. Short and long is the difference between when you use CP and when you use PP. And different industries apply different standards to what defines short and long, and which index do you use in which circumstance. As it relates to the difference between CP and PP, is you'll notice that in the case of CP, we're using the hat notation. So in that particular index, the approximation for the standard deviation is based upon one of those guys. It's not standardized across industries, but since it's an index, the important thing is that you use the same approach every time. So it's unimportant what the absolute value is because you're ranking these. You're saying a process that has a 1.33 is better than a process that has 1.22. And as long as you use the same approach to calculating it, it'll give you the same message regardless of which approximation you use for the standard deviation. Hopefully you recognize the long term is actually the numerical standard deviation that we talked about. And the ones on the right you're thinking are a little weird. They'll look less weird when we get to the section on control terms. Ooh. Excuse me for 1 second. Need to plug my laptop in. It's hungry. Or we'll be looking at a blank screen. Hungry laptop. Okay, so we're looking at this. So we're relating the short term, which we observed, to the long term. And there's these guys working in Motorola in the mid-'80s that basically came up with a best guess for what the difference was between what they could observe on the short term and what they could observe in the long term. And they came up with there's an additional 1.5 standard deviation shift. There's additional variation that they don't see when going from the short term to the long term. Where did they come up with 1.5? Probably because they all had 5 fingers. That's why it's 1.5 and not 1.4. Okay, so frequently you'll hear a company say we're a 6 sigma company or we're a 3.5 sigma company. That's related to the they're quoting out the short-term value. So how many of you have heard 6 sigma corresponding to 3.4 million defects per million opportunities? Well, you have, because I said it when we introduced what 6 sigma was. So they're relating, that actually is based on 4.5 standard deviations from the mean. Why? Because if you observe your process in the short term as being 6 sigma, the real variation when you look at it over the long term is going to be bigger. There's going to be more variation. So the sigma level basically relates to how many standard deviations from the mean is it likely for me to produce a defective product. So you should be familiar with how to convert from long-term to short-term to long-term out to defect level. It's kind of counterintuitive. You will goof it up on the exam, on the practice exams, but you'll learn it by the time we get to the real exam. Okay, so as we relate to process capability, you generally draw process capability out as a histogram, kind of as you can see up there. Because what you're trying to do is you're trying to relate out your spec limits to your distribution. Easiest way to characterize your distribution is with a histogram. These aren't your test results. There weren't enough of you that turned in your exams. But. Okay, so now let's go into the most important part of our course. So we'll labor through this. So now we're actually to lesson 6, which is the stuff that you have. Okay, so in lesson 6, we will meet our most important slide. This will be your most important slide, followed by the hypothesis testing version that looks eerily like it. So we have 2 different types of data. We've talked about this. We have attribute data, which is count type stuff, where if you add decimal points, it doesn't make sense, right? Or it's nominal type values, where yellow 0.2 doesn't make sense. So those are attribute type things. Other common attributes are pass, fail, conformance, non-conformance, attributes. So then we have variable continuous data. Well, that's the stuff you measure. You put it on a scale. Those are the ratio and interval measurements that we labored through. And in a couple weeks, we'll be actually measuring our Subway sandwiches, so we'll get there. So we generally prefer to have variable data, but variable data tends to take longer to collect. It's more expensive to collect as compared to go, no-go. Okay, so the way we generally present data is with control charts. There's a useful way of presenting data is with control charts. The idea with a control chart is to be able to graphically display your data and have it tell a story. And the story you want to tell is that something strange is going on, or something strange is going on. So you have a limited amount of resources, and you want to allocate them to the important stuff. So control charts allow you to screen out the critical few from the trivially many. So they allow you to focus your resources on which one of these observations should I spend the time to investigate what went wrong. Any of you golf? Any golfers? Okay. I'm not much of a golfer, but I hit my 7-iron about 150 yards. Okay. Does that mean every time I swing the golf club with a 7-iron, the ball goes 150 yards?
Average.
Yeah, more or less on average.
No.
No, and if I did do that, I probably wouldn't be standing here. I'd be on the PGA Tour and having a lot more fun and not staring at snow right now. I'd probably be in Palm Beach. So what does that mean? It probably means that on average, I hit the ball 150 yards. Sometimes I'll hit it 130, sometimes I'll hit it 160, right? And that differences could be due to my weight distribution, differences in my grip, the wind, the lie, how I rotate through the swing, all of those things that if you're a golfer, you try to control that variation. what that translates out to our outputs, that the ball goes a different amount, right? Okay, so if I'm out golfing with, I used to pick on Scott Duffy, and unfortunately Scott's no longer here, so I'll have to pick on a generic friend. So if I'm in the middle of my downswing and my friend shouts out their favorite expletive, what's going to happen? Yeah, I'm distracted, and I'm probably not going to impact the ball the same way. It's probably going to trickle off and go about 30 yards. So what a control chart allows me to do, if I'm just looking at the data, to say, hey, that 30-yard hit, something weird happened there. And I can then go investigate it and say, oh, yeah, that's the one I hit when Scott Duffy was shouting out the expletive in the middle of my downswing. It had a assignable cause. Something weird happened. So that's what a control chart allows you to do. It allows you to identify data that's weird. And how weird it is defined by our control limits. So anyone remember what % of the data we expect to see between plus or minus 3 standard deviations from the mean?
Plus or minus 3,
7. Yes. Okay, so our upper and lower control limits in our control charts are set to plus or minus 3 standard deviations from the mean. Okay, so how often do we expect to see an observation above or below the lower or upper control limit due to chance alone?
Good question again?
Yep. So the upper control limit is set to plus 3 standard deviations from the mean.
Yeah.
The lower control limit is set to minus 3 standard deviations from the mean. So our spread is 6 sigma. So we expect there to be 99.7% of our data between our upper and lower control limit. My question to you is, how often do we expect to see an observation outside that range? 0.3, 3 out of 1,000 times. 3 out of 1,000 times, just to chance alone, we expect to see a value either above the upper control limit or below the lower control limit, right? So if we're plotting a control chart and we see a value up there above the upper control limit, well, 3 out of 1,000 times, we just got unlucky. 997 times out of 1,000, something weird happened there. That something weird happening there could be someone miskeyed the number. They put an extra decimal point. It could be, well, the Scott Duffy type example where the operator was distracted and goofed up. It could be they had the balance in grams instead of pounds and ounces. Okay, so in our control chart, what we're doing is we're characterizing the voice of the process. And a control chart is defined by 3 things. The center line, which is generally the mean. And then your upper and lower control limits, which are set by being plus or minus 3 standard deviations from the mean. So it's trying to assign and identify special cause variation. Special cause variation is values that are weird, values that are unlikely to see. There's some assignable cause. And we know there's probably some assignable cause because just a chance alone, we're not going to see a value that weird that frequently. Okay, so our control chart decision tree. The most important slide in the entire slide deck that I will give you. Neon lights, dancing girls, whatever is important to get your attention. Become one with this chart. So the first question this chart asks you is, am I dealing with continuous or attribute data? So am I dealing with measured values, length, width, height, etc., time, or am I dealing with attribute type stuff? So if I'm dealing with measured values, I'm going to go down the left-hand side of the chart, right? So now we get to our next question. Are we dealing with individuals, or are we dealing with grouped data? So in the case of individuals, every observation that I'm evaluating is based upon that individual observation. So I take a part, I measure its length, I record it, I plot it. Those are individuals. The alternative, and so if we're dealing with individuals, we're dealing with the IMR chart, the individual's moving range chart, two different charts grouped together. So the individual chart represents the measure of central tendency. The MR chart measures the amount of dispersion, and you'll see that thematically throughout. So if I'm plotting and observing each individual value, and I'm concerned with each individual observation, I'm using the IMR chart. Okay, but that generates lots of data. And sometimes you can't see the trends you want to based upon looking at every observation. And then we get into, well, subgrouping. So if I were to take all the parts produced today, measure their length, and then average them, and then compare the average today to the average tomorrow 5 weeks ago, then we would be on the other side. So we're dealing with subgroups, right? Monday, Tuesday, Wednesday, Thursday, etc. So they're meaningful subgroups, and we want to compare the difference between the subgroups. Well, in that case, we're going to use the X bar R or the X bar S chart. The difference being, well, the X bar is the same. That's, again, a chart of the central tendency. And the second chart, the measure for dispersion, is either based upon the R. Anyone guess what R stands for? Range. There we go. So it plots the range of the values. And the range is calculated how? Exactly, the highest value minus the lowest value. Cool, so it's really easy to calculate, right? Okay, so then there's the X bar S chart. Anyone want to hazard a guess what the S stands for? Yes, and the standard deviation is kind of a pain in the butt to calculate, right? Okay, so the X bar S and the X bar R chart are used if we have rational subgroups. Rational subgroups being, is there a reason to group the data? Are we concerned with the change in the grouping of the data? Which most often you are. You want to see how the performance is of first shift versus second shift. Okay, so that's dealing with our variable control charts. Then it becomes more fun if we're going on the attributes. So if we're dealing with conformance, non-conformance, pass fail. Okay, so the first question we have is, are we dealing with defectives or defects? This is an important distinction. Defectives relate to conformance, non-conformance. It either is or is not. It either passes or it fails. You can't pass twice, you can't fail twice. You either pass or you fail. Those are the examples of defectives. So if we're dealing with defectives, we're dealing with either the P or the NP chart. These charts are based upon the binomial distribution. Remembering the binomial distribution handles things like coin flips, either heads or tails. Okay, so we're on the extreme right-hand side of our chart. Now our question is, are we dealing with a constant sample size or are we dealing with a variable sample size? So if we're dealing with a constant sample size, we're looking at 100 units today, 100 units tomorrow, 100 units the next day. That's a constant sample size, right? We can either use the P chart or the NP chart. So the P chart represents the proportion of defective, and the NP chart represents the number of defective. Okay, so if we have a variable sample size, which tends to be the case, if you're looking at the proportion of defective products produced today, and you produce 100, and tomorrow you produce 150, if I plotted the number of defectives, it would mean something very different. So in the first case, it would be 5 out of 100, so 5%. And if I got 5 defectives the next day, it would be 5 out of 150. Is 5 out of 100 the same as 5 out of 150? No. So plotting an NP chart wouldn't make sense there because it would just plot 5. The P chart, on the other hand, looks at the proportion. So is the proportion of 5 out of 100 the same as the proportion of 5 out of 150? No. So it captures that. And if you're a baseball fan, this is why we generally have batting average and the number of hits, right? The number of hits is just a count statistic. The batting average is a rate statistic. So in this case, the proportion is the rate. The NP is the count, just how many defectives we produced. Okay, so that was defectives. Now we're going to go over to the alternate, defects. So defects are any nonconformance. And a product can have lots of defects. So this also relates to count type stuff, right? So you can use these type of charts on the number of products produced. You can't produce a fractional product. The number of customers you service. You can't service a fractional customer. Okay. So then we are using the C or the U chart. And again, the next question is, are we dealing with constant sample size or variable sample size? If we're using constant sample size, we can use the C chart. And again, it's a count. So how many customers showed up at Starbucks? Okay, 57 in an hour. Okay, then in an hour tomorrow, same hour tomorrow, 58 showed up. Okay, that's a meaningful comparison from 57 in an hour to 58 in an hour. If on the third day, only observed for half an hour and 29 showed up, is that a meaningful comparison? 57, 58, 29? No, because I only look for half the period of time. It's a different opportunity size. So in that case, we would have to use the U chart, which is looking at the average number per unit. Cool? We'll go into these in a lot more detail.
Can you do that one again, the I versus the IMR?
Yep, right there. Next slide. Great transition. Thank you. Okay, so in all of our measured control charts, we'll see that there's two charts. There's an upper chart and a lower chart. The upper is measuring the measures of central tendency, so the mean, and the lower is measuring the dispersion. Told you we would get back to that stuff and keep coming up. So in the top graph, the eye chart, which is not what the doctor has you cover one eye and read off the chart. Remember the deal. You don't have to laugh, but you do have to give me evil looks to make sure you're paying attention. So in the upper graph, we're taking each observation. So I measure a product, I find its length, I plot it. I measure the next product, I plot it. Repeat as at will. No one here is named Will, so okay, repeat that at will. Okay. So we're cool with what the top chart represents. Yes? The bottom chart is our measure of dispersion. And when I'm looking at individuals, well, it's not like I can calculate out the range. I can't calculate out the standard deviation. But I can look at the differences between observations. My process shouldn't be bouncing all over. I shouldn't produce a really big piece and then a really small piece. So the MR chart, the bottom chart, represents the difference between observed values. So the first plot here is the difference between observation 1 and observation 2. The second dot represents the difference between observation 2 and 3, etc. That makes sense?
The eye chart, why does it say MRI table? One's an eye chart, one's an MRI table.
Well, the top is the eye chart, and the bottom is the MR. They're always shown together. So
Okay, so the MR chart, the top one, the MR chart.
is the bottom part of the IMR chart is both charts together. The top part of the IMR chart is the eye chart. The bottom part is the MR chart.
But the MR chart is the one that it measures the difference between it. So if you got 3 and 5, you would plot 2.
Bingo, and you can see that right there, where it's the moving range.
Okay.
So the top chart is the individual value chart. The bottom chart is the moving range. Okay, so there are formulas to calculate out your upper and lower control limit. There's also a formula to calculate out the center line. Anyone know what the formula is for the center line for the eye chart?
No.
It's the average. No, the eye chart is the individuals. So the center line, our prediction of what the center is the mean, right? And how do we calculate out the mean? We take every observation, we divide by the number of observations. It says for x bar. So x bar is our center line. Then to calculate out the upper and lower control limits, well, we see that the upper control limit is the average, x bar, plus E2 times MR bar. Okay, so what's MR bar? Okay, so MR bar is the center line of our moving range chart. So moving range is the difference between observation 1, observation 2, observation 2, observation 3. So I calculate out those differences and I average them. That gives us MR bar. And then E2. constant from the back.
Which one?
It's a constant from the back of the book on page 369. So anyone have their book on them? Anything handy? Because you also see on page 368, there's a really important page. 369 and 368. Hopefully they're on the same page. Not the same. Same binding over. We're just going to be on there, but they can see it on the phone.
No, that's good.
Okay. So you see on page 368, right? You should be familiar with what's on 368. There are all the formulas for the control charts in one nice, easy page. Okay, then going on to page 369, we see that we have a chart, right? We have some nifty chart. And can anyone find the E2 constant? Yep. Yes, you might want to highlight that on the IMR chart or write it in directly. The E2 constant for the IMR chart and the IMR chart alone will always be 2.66.
The E2, 368.
Yep, 368 has all the control chart formulas, and 369 has the control chart constants.
Which one did you say we were doing?
I'm saying for the IMR chart, it's asking for the E2 constant,
Yes.
and since your sample size is always 2, because we're looking at successive values, it's always going to be 2.66. But that's only for the I chart. Yeah, it's 2 samples because what we're doing is we're looking at this one observation to the next, and that's what we're plotting. So that's why it's 2. But since the IMR chart always is 2, it's always 2.66. We'll see that we use the E2 constant for the other control charts when we get there. Okay, moving on to the X bar R. Remembering now we're dealing with, instead of plotting the individual observations, we're now moving on to the case where we have a rational subgroup, where we've grouped our observations, and we want to see the difference between the groups. So I take my observations on Monday, I plot it. I take my observations on Tuesday, I plot it. Wednesday, Thursday, Friday, etc. So that's when we use the X bar R or the X bar S chart. Okay. So our top chart, the X bar chart, is plotting those averages. So I average Monday, I plot it. I average Tuesday, I plot it. I average Wednesday, I plot it. Our center line here is the average of the averages. So the average of Monday, average of Tuesday, Wednesday, Thursday, Friday, etc. That's our center line. The bottom chart is the range chart. So I take the range from Monday, I plot it. I take the range from Tuesday, I plot it. I take the range from Wednesday, I plot it. So the R bar there, the center line of the R chart, is just the average of the range. Unfortunately, in math speak, it looks really yucky. But all it is it's the average of the daily ranges. So where do our upper and lower control limits come from? Well, our center line of the X bar chart is just the average of the averages. The upper control limit is the average plus A2 R bar, where R bar is just the average of the ranges. And A2 comes from page 369. And this time you actually have to look at what your sample size is, right? How many observations went into Monday's observations versus Tuesday's versus Wednesday's versus Thursday's. And frequently you'll see that your upper and lower control limits are in a straight line because your sample size isn't the same every day. And you'll see them vary a little bit. Cool. Now we have our X bar S chart. So our X bar R and the X bar S, the top chart's going to look exactly the same because it's plotting the same values. The difference is the bottom chart, instead of plotting the range as our measure of dispersion, we're plotting the standard deviation. It turned out when people were doing these by hand, it was much easier to calculate out the range than it was to calculate out the standard deviation. Now that computers generally do the calculations, Minitab doing a very nice job of it, it doesn't really matter for the computer to crunch out the standard deviation versus the range. But there are some circumstances where you use the range, with a small sample size. The standard deviation is kind of meaningless if you have 3 observations, 5 observations. The range still is meaningful. Okay, so again, the bottom chart is plotting the standard deviation. So I calculate out the standard deviation for Monday. I calculate out the standard deviation for Tuesday, Wednesday, etc. The center line, S bar, is just the average of the daily standard deviations. Cool. And then once you know S bar, you look up the constant and you multiply to calculate out your upper and lower control limits. Cool. Okay, so now we're flipping over to our attribute charts. And the exam will try to trip you up every which way from Sunday on the difference between defects and defectives. So be careful, you've been warned. So a defective is a non-conformance. It either starts or it doesn't. Turn the key on my car, it either turns on or it doesn't. Doesn't turn on, it's defective. Defects, are, on the other hand, are any non-conformance. So those of you who know my car knows there's lots of scrapes and dings and dents in it, right? Each example of those is an example of a defect, right? It's a non-conformance. Okay, thinking question. If something has a defect, is it necessarily defective? Everyone agree?
What did you say? No.
The question was, if something has a defect, is it necessarily defective? Okay. So my car has lots of scrapes in it, right?
Right.
You've seen my car.
I've never seen it.
Well, you're aware that my high schoolers thought that the reason I don't have a girlfriend is because I drive the same car I did in high school. It's a 1998 Subaru Legacy wagon with 300,000 miles on it. It has a few scrapes in it. Plus, I put kayaks on the roof, and I have roof racks, so the roof's scraped. But it doesn't get stolen in Camden. Okay, so each one of those scrapes is an example of a defect.
So no, it doesn't have to be defective.
Correct. As long as it starts in the morning, I'm happy. Okay, now let's flip the question around. And this is where the exam will try to trip you up. If something is defective, does it necessarily have to have at least one defect?
Yes. Yeah.
Yes. So however you need to process that internally to make sure you have that relationship down cold, please do it. So for me, the car example works. If a better example works for you internally, go for it. I'll park it in the snowbank. Exactly. Maybe I'll put a slide of my car. I'll put a picture of my car, since you guys learn way too much about me. And now the YouTube audience gets to learn about me.
Brian Cars has a lot of defects, but it's still not defective. Because it starts.
Exactly. It starts and goes.
It goes from place to
It goes from place to place and doesn't get stolen. And again, we'll keep coming back to the CTQs, the things that are critical to quality. And quality is defined as who your customer is. So if I'm the customer of my car, which absolutely I am, I'm the one who gets to drive it around, if it gets from point A to point B and doesn't get stolen, I'm happy.
So you like your defects.
I personally think that if I'm a car thief and I'm going to go to jail for the same amount of time for stealing car 1 that looks like mine or a brand new BMW, I'd much rather steal a brand new BMW. But I'm assuming that car thieves think like me, and I wouldn't be stealing a car, so bad premise, but get the idea. So the idea here is that defectives are conforming, non-conforming. Works, doesn't work. Can only fail once, can only pass once. Defects, on the other hand, is any non-conformance, so there could be lots of problems with it. Okay, so our first defective chart, the chart isn't defective, but it relates to defectives. Conformance, non-conformance, is the P chart. So the P chart is just the proportion of defectives. So P bar is the total number of defectives divided by the number of observations, number of units. That's pretty straightforward there. And the upper and lower control limits are set to 3 standard deviations. However, in the case of the P-chart, it's based upon the binomial distribution, so it's a different approximation for the standard deviation. So, cool. Oh, important point. You can use these to be optimistic or pessimistic. By that, I mean that you can use a P-chart for the proportion of defective or the proportion of good parts. So you can do it on the proportion of conforming, so you can do 0.9, or you can do it on the proportion of non-conforming, 0.1. Remembering back to when we went over probability is that you can look at probability either as the probability of it happening or 1 minus the probability of it not happening. So since it's either 2 outcomes, either passes or it fails, you can either look at the glass as half empty or half full. You're not allowed to just drink the glass, or break the glass, or freeze the glass, or change the volume of the glass, or any other smart alecky type answer to is that glass half empty or half full. Cool? Because the exam will try to trip you up that way. And some people will get confused because they'll be looking at the proportion of conforming parts and will say, well, I can only use a P-chart for non-conforming. The math doesn't care. Okay, so the NP chart. So in the case of the P chart, we're looking at the proportion of defective. So like 5% defective, 10% defective, 90% good. That's the P chart. The NP chart is looking at just the number. So the number of good products produced today, the number of good products produced tomorrow, the number of defects, the number of units on sterility hold would be done on a P chart, on the NP chart. N representing the number. Cool. C chart. So the C chart relates to defects. So these are things that can happen more than once. You can have more than one customer arrive per hour. You can produce more than one piece per hour. You can have more than one CFU per product. Hopefully. So if our opportunity size is always the same, we can use the C chart because that represents the count. So there's 3 defects, 4 defects, 5 defects. So if our unit is car, so I can plot the number of defects on my car and count the defects on the next car, etc. Right? But if I was using a variable sample size, so it's the number of defects produced today, we might not be able to get that relationship because that might be 12 cars, it might be 5 cars, it might be 3 cars. You might not have that meaningful relationship. The C chart relates to a circumstance where you have a constant sample size. So you're always looking at 1 unit, the number of defects per unit. Perfect example of a C chart. The U chart, on the other hand, relates to the circumstance where you have a variable sample size, where you're not always looking at the same amount of opportunity size. So with the C chart, another common circumstance you have is like defects per foot. Per foot being constant, foot is always a foot. Cool. How are we doing on time? We are out of time. Any questions for me? This is the most important stuff that we will go over. So we will finish up with this next class, and we'll actually have you guys start to use it and calculate it out based on your exam scores. But if there's any point that I can emphasize as being the most important slide deck in the entire class, it's this. You can expect to see 10 questions on the exam as to which control chart to use in this circumstance, calculate out the upper control limit for a C chart. This is the most important set of slides we will go over. So make sure that you're able to tell the difference between defective and defects and be able to understand the difference between when you use an I chart versus the X bar R or the X bar S chart. If you can do that, you just got 10 questions on the exam. Cool. See you guys next week.